nuts that most statisticians at this stage in the game when you're learning about this don't talk about it. This is what drives me nuts. So Carly, you always told me, and I love this, I like 99% confidence. I like being confident. And as an English word, the word confident, it sounds good, yes? Confident. What else sounds good? Does the word power sound good to you? Power sounds good. As an English word, power. Power sound good? Maybe it corrupts. We often hear that. Absolute power corrupts absolutely. But power and confidence have statistical meanings. Confidence is the complement, to use your word, perfect word, of what's called significance. Significance. So confidence, we're at 95% confidence very often. That means we're 5% significant. That's the rest of the tail. That's why whenever we talk about a type 1 error, we talk about what's the chance of a type 1 error? Well, assuming we're at 95% confidence, the chance of a type 1 error is therefore, by definition, 5%, because that's what we're testing against. What's the Greek letter for a type 2 error? Remember that from yesterday? Beta. What's the value of beta? Trick question. Trick question. Trick question. Trick question. Why should you not answer it? Because you can't answer it. You're about to see why right now. How are alpha and beta related to each other? As alpha, as alpha goes up, beta goes down. And what's the complement of beta? Power. Let's come back to all this. Let's make sure we understand all this. Okay? So, here's the deal. Now just bear with me, friends. Bear with me. Here is a null hypothesis curve. Please bear with me. Do you see how I've placed the null hypothesis with the little 5% region or ish on the right side versus the left side? It's kind of the opposite curve of what we've been talking about today. That doesn't matter. They can be on either side. The same logic applies. So you see what you can do is you can then adjust your confidence. Make this a little bigger so you can see it. You can adjust your confidence by where you put your cutoff value, yes? If you put your cutoff value close to about 1.645, is there 1.645, Blake? That puts about 5%. Excel's kind of annoying. It won't let me get it exactly 5%, but it gets close to it. So if I slap this guy right about at 1.645, 5% this side, 95% this side. If you can, imagine it reversed. It would be the exact same thing, but on this side. Is that fair? Okay, good. So here's the deal. We select where this goes, correct? We select that comma. So Carly, where would you put yours? You put yours further right, correct? So if that's where you would put yours, Carly, thank you for that. What would this number then be up here? The chance of a type 1 error, or the significance would be 1%. Say that's loud, be brave.
1%?
Yes! Let's see how close I can get. That's not bad. It's about 2.575, if I remember correctly. That's the z-score value. Okay? Now, of course, this can all be edited with sample size. We'll come back to that momentarily. But here's the problem. This is your null curve. This is the curve you know something about. So you know where the center of this curve is. In our example we're doing right now, it's 12%. That's our example, 12%. You know where the center of this is depending on what you're studying. Airborne, Allegra, seasonal allergies, whatever. It's got a center. What don't you know the center of? The other hypothesis has a curve too. The research hypothesis has one, right? It has a curve too. Now the problem is, you don't know where that thing is. It's somewhere. It's somewhere. And here's the kicker. Here's the kicker. When you, Carly, move that critical value, you also move that critical value on this curve, wherever that curve is. That has to happen. You're only doing one study. You're deriving one value from that one study. It has to count for both curves. Now what's tricky is, it's hard to know where this curve lies with respect to the other one. So what we're going to do, put them together. Here they are, both together. Now, I just slapped down the alternative curve on the right of the null curve. We don't exactly know where it is. It's out there somewhere, so I've made it so you can move it. I've made it so you can move it. So here we go. We can move it to the right. We can move it to the left. This is all supposition at this point, correct? Because we don't know where it actually is. It's out there. The one we know is fixed is that red curve, the null curve. Now Carly, and everybody for that matter, you see those blue and orange areas right there? Blue and orange areas?
Okay.
The blue area is the chance of a type 2 error, which would be a false negative. That means we did a study, we got negative test results, which means we think it lies on the other curve, the null curve, which would be failing to cry wolf. No wolves here. No wolves here. Failing to cry wolf. Drug doesn't work. In fact, it does. The orange is a chance of a type 1 error. Carly, this is why I'm careful about 99% confidence. Watch what happens to type 2 error if we shrink type 1 error. Are you guys beginning to see what happens to it? Ignore the numbers. The numbers, Excel's pissing me off as I get too big. But you see the big idea? As type 1 error shrinks, type 2 error necessarily grows. So you have to decide at the beginning of your study. Please ignore the percentages. I haven't figured that out yet with Excel. I can't fix that yet. But the idea is the areas. The areas are irrelevant. You can look at the areas and understand orange is way smaller than blue. So the idea is you have to go into the study deciding which kind of error you want to avoid the most. You want to avoid... So those of you that were saying, I don't want to make a type 2 error, I don't want to make a type 2 error,
you don't want blue.
That means you want less blue. So Carly, you actually, if you want to definitely avoid a type 2 error, you'd probably be okay at like 90 or 85% confidence. Because that knocks down the chance of screwing up with a type 2. If you guys want to definitely avoid a type 1, then you shove that 99 as far to that tail as you can and you forget type 2. This is a case-by-case basis. There's no textbook definition for which one's worse. It varies on a case-by-case basis. A false positive sometimes is worse, a false negative is sometimes worse. Okay, as a rock climber, if I clip into a harness 1,000 feet off the deck, I want to know that that loop that I'm clipped into is actually going to hold. Yes? So which kind, if they're doing tests on that gear loop that I'm hanging back from, right, what kind of error would they want to avoid the most? Think about that. Put that in the back of your mind. That's going to be, we're going to come to that later. Think about which kind of error would be worse, because what I don't want to have it do is snap. Right, so think about that. Plant that in the back of your mind. It changes from context to context. I've got lots of examples coming. Keep it in the back of your mind. Keep it in the back of your mind. I want you guys to think about it. Thank you for the votes. Veronica, go.
I have a question. So,
yes.
Since you have to determine this before you start, and I haven't tested this pill.
Yes, you haven't.
And I find out that it has, I choose my confidence.
You choose your confidence.
And then I find out that it has some pretty extreme side effects.
Oh, good.
So I want to replicate the test. Can I change my...
The side effects, in effect, have to have their own test to go along with those. So you've opened a can of worms now. Because no longer are you going to do a test on just the efficacy of the vaccine, but also the side effects of the vaccine.
Yes.
So you've opened a potential Pandora's box.
Yeah, but my question is, if I want to change the test because I've decided to change the type of error...
Oh, I see what you're saying!
Oh. Can I change my confidence interval and replicate the study as that of...
It wouldn't be a replication anymore, would it? It would be doing the study again, but it's essentially starting from scratch.
And so is that where that falls in, where you have different confidence intervals?
Oh, for sure.
To that power and...
Yes,
confidence?
except you would basically be starting over from scratch, so you'd be back to 1. And to hear what Veronica just said, she just made a very important connection between what we're doing right now and what you were just doing on one of the questions on that exam that said if you do 51 confidence intervals, all at 95% confidence, what's the chance that you're right in every single one? It's almost 0, right? 7%, I think I saw a couple of you guys write down, right? What we're trying to do is minimize that by collecting them all under one umbrella of testing. We haven't quite gotten there yet. That's where the M&Ms come in later on.
Okay.
But no, I love what you've just opened up a huge Pandora's box.
I'm just still trying to figure that out.
Don't you worry about it. One step at a time. Okay. Right now, just trying to see which way would we rather screw up. If you're okay with a type 2 error, if you don't care about a type 2 error at all, then Carly, go to 99.999% confidence. Because that'll shrink that down to basically 0. But if you want to avoid a type 2, definitely avoid a type 2, you're going to have to accept lower confidence. Mathematically, this is... Now, I take that, hold that question for just a second if you don't mind. There is one way you can minimize them both simultaneously. And you know the answer to this, but you probably forgot it already. Watch this.
Hypotheses further apart.
Well, let me come back to that. Here's what you have control over. Your sample size. Right? If you increase your sample size, the sampling curves are going to get taller and skinnier. Critical values in the same place. Therefore, the tails are going to shrink. Now, Blake's got a very good point, but the problem is we don't have control over that, Blake. That's something we don't have control over. He said, oh, dude, make your curves further apart. You know, make it, here, look at that. Look at that, that blue just shrunk away all by itself. Yes, that's true, except I can't control where that other curve is. Right, it's out there, and I'm trying to find it, but I can't control where it is. I can control how many I sample, though, which is why the FDA does 40 and 50 and 60,000 N equals 40, 50, 60,000 on their trials. So you can shrink those curves down as tight as possible. So this is why I care about errors, because you can mitigate errors by how large your samples are, yes?
Yeah.
Makes sense? I have a quiz that centers around this exact spreadsheet. We'll do it in a couple weeks. I'm going to have the spreadsheet for you to analyze, open it up, mess with the bars, and let that point kind of drive home again. Fair? So that's why, Carly, I had to wait 2 weeks. I apologize. Confidence, 99, it always sounds confident. Yeah, confidence is great.
Yeah.
But so is power, which is the chance of a true negative, or excuse me, a true positive. Finding an effect that works is the power of a test. The effect is there and you correctly identify it. Power. Confidence is great. It's saying I'm correct in that nothing happened. Right? Correct that nothing happened. Confidence is like, yes, the vaccine does not work and I am correct in saying it doesn't work. That's a negative test result and I'm correct, so it's a true negative. This is a true positive. The vaccine does work and I found it. You see how that can be more powerful? That's how drugs get released. That's why Claritin is on shelves. Because people think they found a true positive, a true change. Fair? Sorry, it's a little overwhelming, I know, especially all at once at 9:30 in the morning. But that's the important, that's why I didn't want to let that go. I didn't want to let that go. So, all right, back to here. So the question, of course, is